Welcome to part 2 of stress, strain, and faults. This is video earthquake 10b.2. We are currently on the third bullet, 3 kinds of faults. And you did already see a video on faults that introduced them. So this is going to be a quick overview that you can always come back to for review purposes. So the 2 groups of faults are the dip-slip faults and the strike-slip faults. And the dip-slip faults, like they sound, have a dip. Okay, so either side of the fault is moving along a slanted or an inclined break in the rock. On the other hand, the strike-slip faults are vertical. So we're going to look at these 2 groups. We're going to start with the dip-slip faults. And we want to talk about which side of the fault went up relative to the other side, or which side went down relative to the other side. And so the convention has been taken from the mining days because mines often occur along ancient fault zones. It makes pathways for water to go and minerals to accumulate. So if a mine tunnel happened to go across a fault like this, the miner would put their lantern up above them and they would call that side of the fault the hanging wall because that's where their lantern was hanging. Their feet, on the other hand, would be below them. That would be the footwall block below the fault. So we always look at the hanging wall and the footwall as the 2 sides of a dip-slip fault. Now, if we look here, you can see from these rock units that have been drawn in that there's been offset across the fault. So all of these rocks were once horizontal and continuous. Picture the Grand Canyon. So this lighter colored one, let's just pick this one. It used to be continuous. It used to go all the way up like this. But along the fault, it has been broken. And the hanging wall block has gone down relative to the footwall block. You can either figure this out by looking at the arrows, if there's arrows on a diagram, or by looking at the rocks themselves and seeing which side went down relative to the other. Another thing shown here is a fault scarp, which is the surface expression of a fault if the fault happens to rupture at the surface. So for dip-slip faults, we have 2 kinds. One, the hanging wall goes down relative to the footwall, and the other one, the hanging wall goes up relative to the footwall. So here is what we call a normal fault. The hanging wall goes down relative to the footwall. And again, you've got arrows showing this. Or you could look at this package of rocks, right? There's 4 layers here, and on the other side of the fault, they're all lower in elevation, right? They've gone down. And so this is a normal fault. Notice the arrows here, these are indicating tensional stress. So tensional stress causes normal faulting. And one way to remember normal is if you imagine that this fault surface was actually a hill, and you rolled a ball down it, a ball would naturally roll down the hill because of gravity, right? So normal fault, the hanging wall goes down. That's what gravity would normally do. On the other hand, if we look at a reverse fault, here we have the hanging wall going up, and you wouldn't normally have a ball roll up a hill. Now notice that the hanging wall is on the left, footwall's on the right. In the previous one, that we're in opposite locations, because it doesn't matter which side they're on, it only matters which side is above the fault and which side is below. The arrows here are showing us compressional stress, and this is a reverse fault with the hanging wall going up and over the footwall. Again, you can look at arrows if they're drawn on the diagram, or you can look at the rock units and see how they have been altered. Now, a special kind of reverse fault is called a thrust fault, and it is still a reverse fault, but instead of being somewhat steep, it's actually very shallow. It's very close to horizontal, but it's still a reverse fault. We still have the hanging wall going up and over. I'm not going to use the term thrust fault in this class. I don't expect you to worry about this little difference. So normal and reverse faults are the only dip-slip faults I want you to know. Let's move on to strike-slip faults. Now notice, because these are vertical, there are no hanging walls or footwalls. The only thing we need to decide about strike-slip faults is whether or not they are left lateral or right lateral. And the way you tell that is this. So we have arrows on this one, And those are telling us that if we were on this side of the fault and we looked across, the other side moved to the left. However, if we were on this side and looked across, the other side moved, also to the left. So this is a left lateral strike slip fault. No matter what side of the fault you're on, the other side moved to the left. Now, if you don't have arrows, you might actually have something like a river or a stream or a road that is offset. So if you were driving along this road towards the fault, then suddenly the fault broke the road and you would have to go way over to the left to continue on the road. On the other hand, we have right lateral strike slip faults. So those are the two kinds of strike slip faults. So 4 faults altogether that I want you to learn. So now it's your turn to see how you do looking at faults from the field. So what kind of fault is this? First of all, we are looking at a side view, like a cliff, a road cut. So you could be standing next to this and looking at it. It's hard to tell. It might look like a map view, but it's not a map view. So the fault's been emphasized in red. Some offset layers are in green. And the first question you ask is it strike slip or dip slip? Because it's not a vertical fault. It's pretty steep, but it is dipping. It's a dip slip fault. So the best way to determine the hanging in footwall is to put your finger or a dot on the fault, draw a vertical line up, and that is the hanging wall. The hanging wall is above the fault. Draw a vertical line down, and that is the footwall. So here you can see the offset layers, and hopefully you can see that the hanging wall has gone down relative to the footwall. So what kind of fault is this? A normal dip slip fault. Here's another one with yours truly in the picture, and there's a fault behind me offsetting some tilted rocks. I will highlight it in green so you can maybe see it, and I'll remove that again. So there's the big break, and you can see that there are some rocks that are offset. In particular, these darker units here are offset. So once again, let's figure out strike slip or dip slip. Well, the fault again is pretty steep, pretty close to vertical, but it is dipping. So let's go ahead and figure out where the hanging wall is. It's going to be above the fault, and the footwall will be below it. Now this is an interesting picture because it's hard to tell how big this fault is behind me or how big these rocks are. You might look and say, oh, well, I guess maybe in this little shadow here I could wedge my shoe under there, right? But actually this is much farther in the distance than it looks. So let me show you a different perspective. So here's that exact same picture I just showed you. And then here's also the same picture pretty much, but without me in it. And then there's somebody standing there. And that little shaded spot was over here. So this is actually a much larger scale fault than it appeared in the first picture. So what did you think? What kind of dip slip fault is this? Normal dip slip. Good. Now here's a rock with a fault in it. So we can have small faults. We can even have something called micro faults. So faults don't have to be big all the time. And I'm going to just tell you that this is a dipping fault. So first question, which side is the hanging wall and which side is the footwall? Hanging wall, footwall, which side went up? The hanging wall went up. So this is a reverse dip slip. Now this one is kind of tricky. I'm going to tell you it is a strike slip fault, and the fault runs through like this. So if you're driving your car right here and then you get to the fault and you say, uh-oh, where'd my road go? It went to the right. And the same would happen if you were coming from this direction and you got to the fault. My road went to my right. So this is a right lateral strike slip fault. Here's another road cut type fault. I'll show you where the fault is. It is dipping. So we have to figure out the hanging wall, the footwall, and which side went down. There's some arrows to show you that offset brown unit. And this is a normal dip slip fault. Notice the hanging wall's on the left here and the footwall's on the right. This happens to be the San Andreas fault. I'll show you with that pink line where the trace of the fault is. And I'll take it away for a moment. So we have some hills over here called the Temblor Range. We have streams coming out. And when they hit the fault, they have been diverted along the fault and they continue here. So this stream once went straight Streams don't usually take right-hand turns or left-hand turns. So what kind of fault is this? And I guess I will tell you it is a strike-slip fault. So that is the motion of the fault. Right lateral strike-slip fault. Now here is a geologist's sketch of that same image, and here are the mountains. This is where the creek took a sharp turn along the fault, and the arrows are showing that it's a right lateral strike-slip fault. Now I have another picture of me, different field trip, but same hat, and here I am standing right about where that arrow is, where it says creek bed, right about there. And so in front of me here is the creek that goes up into the hills. And then right along here, this very linear valley is along the San Andreas. And then you can see it takes a sharp left turn, and that's where the creek bed goes down there. Okay, in the last video, I asked you about a picture and said what kind of stress and strain formed it. So take a look at this one and see if you can figure out the type of stress, the type of strain. Okay, so the type of strain is brittle. Remember, faults are broken deformation. They're brittle strain. And these faults happen to be normal faults, if you can see these arrows, or you could even look at this dark layer and see that the hanging wall has gone down relative to the footwall. So normal faults are created in regions of tension. The last thing we're going to do is put all of this together and link it to plate boundaries. So just as a reminder, we have three kinds of plate boundaries: divergent, where plates move apart; convergent, where plates move together; and transform, where plates move side to side. So what I'd like you to do is make a little table in your notes, and in the first column, you're going to put plate boundary at the top, and you're going to put divergent, convergent, and transform. Then you'll have a column labeled stress and a column labeled fault type, and we'll put all of these things together. So divergent plate boundaries are places where we have plates moving apart from each other, and so that is created by tension. What kind of fault do we have? Well, we have a dip-slip fault. Hopefully you recognize that. Now, where's the hanging wall and where's the footwall? There we go. And the hanging wall seems to have gone down, so this is a normal fault. So on your chart, for divergent plate boundaries, the stress that creates these types of boundaries is tension, and the fault type that would be created would be normal dip-slip. For convergent plate boundaries, we have things pushing together, and that is compression. And you can see, once again, we have a dip-slip fault. So where are the hanging wall and footwalls? This is a reverse fault. So you can put this now in your table. Convergent plate boundaries are created by compression and tend to have reverse dip-slip faults. Finally, we have the transform boundaries. These are created by shear stress, and these are strike-slip faults. So pause the video for a moment and think about which one of these is left lateral and which one of these is right lateral. All right, here are the answers. Oh, I put a little stream there to kind of maybe help you. Right lateral on the left and left lateral on the right. Ooh, that's kind of backwards, isn't it? Shouldn't have done that. Okay, so here is our completed table with all of our information. Transform boundaries are created by shear stress and create strike-slip faults. Finally, we are back at our original questions. Looking at these mountains, hopefully you can now answer these questions. What kind of stress creates plate boundaries with mountains? Compression. What kind of faults would we expect in a region of compression? Reverse dip-slip. And finally, what kind of plate boundary probably produced these? Convergent. And that is stress, strain, and faults.